So, hello everyone, once again to the second episode of this podcast, which still doesn't have a proper name, but we continue on inviting a new guest who is at their PhD level working on the big questions of this universe. And today I have someone who is working on a topic that interests everyone, piques everyone's curiosity when the word is thrown around. It's there in every Marvel movie and it excites everyone all the way from the first year UG students to the CEO of Google. So I'm talking about quantum computing. And today I have Vyom Kulkarni, who is a second year PhD candidate at Chalmers University, Sweden, working on quantum computing.
Yeah.
Welcome.
Hi.
Hello.
Hi, Kapil. How are you doing?
Yeah, good. My annual review is coming up soon,
Okay. Yeah.
which will be my the candidature deciding process. After which I'm kind of assured, but then I'll have to, go through the usual PhD process of publishing papers
Okay.
and all that.
Yeah.
Uh, but yeah, it's going to be 1 year here in Australia for me.
Nice. Nice. Yeah. My
How have
my annual review also happened quite recently.
how was
Uh,
that?
it went well.
Done well,
It went well,
okay.
thankfully.
Gives confidence.
Yeah.
So yeah, it's like until the deadline comes close, you kind of are not that scared, but then you realize that it's nearing
Yeah.
and you need to
Yeah.
get things done.
Yeah.
Uh,
Yeah.
okay, so coming to your work, I wanted to ask, you're dealing with such a buzzword and a big field of research right at the moment. So when you meet people, when you meet your relatives, when you go back home, how do you explain or tell what you're exactly doing at Sweden?
Yeah. So it's a little bit hard to explain. I haven't quite figured out how to do that. Explain it in like very lay terms. Uh, but yeah, it all yeah, I have to it begins with like starting to explain a bit of quantum mechanics and how it is different from the world that is normally visible around us. And then I can talk a bit about how that relates to the work I'm doing and how I'm trying to achieve that experimentally.
So
Uh,
now that we have the time here, so we
yes.
can start from the basics itself. It'll be nice to start off with a primer on quantum mechanics, then move into what is a quantum computer, and then
Okay.
exactly where your field of research is aligning to.
Yeah. Yeah. I think
Yeah.
yeah, that's a good way to go about it.
Right. So
So yes, let's
so what
start
do you
from
want to start off as the basics? What exactly is quantum mechanics?
Yeah, let's start from that. What exactly is quantum mechanics? I think people are still trying to figure
It's a
it out.
big question.
Uh, but yeah, so quantum mechanics was like a very new theory of physics almost a century ago. It was discovered in the early 1920s, mainly in Germany. Yeah, what it says is that the world at the smallest scale, so at the level of the atoms, or even smaller at like protons, electrons, neutrons, and even smaller levels than that, all of it is explained by a completely different set of laws called quantum mechanics. And this is super different from like the normal world of sticks and stones that we see around us. And the way it is different is that uh, the particles, when they are like very tiny, when they are explained by quantum mechanics, they have quantized energy levels, which means that they can only have certain energies. So they can have, say, let's say, 1 unit of energy, or 2 unit of energy, or 3 unit of energy. It can never have 1.22 or 1.23 units of energy. So that is like the or one of the main points of quantum mechanics. And this is this directly leads to quantum computing because then you act on these energy levels, as they are called. So these units of energies that particles can have. And you try to act on these energy levels and use them for certain computing tasks. So now, okay, let's say for classical computing, so the computers that we are all very familiar with now, you talk about bits which are 0 and 1. So it can either be in the zero state or in the one state. So it's similar with to what what happens in quantum mechanics. You have these quantized energy levels. So you can have a particle in energy level 1 and you can have a particle in energy level 2. And these act like bits, except that they have certain different properties that make them useful for
Hmm.
certain tasks.
So quantum mechanics kind of says that the universe at the lower scale is like a pixelated version of what we see at
Yeah,
the larger scale.
yeah,
That's usually the analogy given.
yeah,
And because of these differences in energies, it's fixed. Either you get a zero or a one.
exactly.
You can use it in the same way that we use a regular computer, which has transistors and working in the zeros and ones.
Yeah,
So now that we know what quantum mechanics is, I guess that's weird to say.
yeah, now we know what it is.
And the now that there's a basic definition of a quantum computer given, so how exactly is your experimental work uh, guiding to a quantum computer, but not exactly working on a quantum computer? That's what your intro said.
Yeah, okay. Before I go into that, it seems like I will have to give another primer
Primer.
on, yes,
Okay.
it's primer number two today.
Backstory too.
Yeah, so now we will talk about superconductivity, which is a
Yes.
related concept, but somewhat easier to explain. So I think people might be familiar with resistance already. So if you hook up a battery to say a iron rod, it will offer some resistance to the current flowing through it. Superconductors, when they are also metals, so they also have a lot of electrons just hanging around. But if you cool them down to very low temperatures, so temperatures around 1 Kelvin, which is minus 270 degrees Celsius, so very, very, very cold. And if you can cool them down to below that temperature, then what happens is that they no longer offer any resistance. So if you send a current through it, it will flow through without having any resistance to it. And this is a very quantum mechanical phenomena. So the things that I explained about having quantized energy levels and so on, all those things directly lead to superconductivity also. And because they are related, you can use these superconducting systems to study quantum mechanics. And that is exactly what I do. Uh, yeah, so okay, to get into the technical details, what we do is we make circuits out of these superconductors. So yeah, they're very similar to printed circuit boards, which are very common nowadays, or like transistors and stuff. But these are made with superconductors. So the component of resistance is eliminated. And with the
Right.
remaining elements, called, so capacitors, inductors, and so on, you make circuits, and these circuits behave quantum mechanically. And you can study quantum mechanics or quantum optics using these systems.
So can I say it's like a larger version of a more smaller system that you can handle? It's like superconductors are something like in a physical. It's a
Yeah.
big object, so you can kind of handle it rather than at the atomic level. Uh, so can you call it an analog of a quantum computer, or can you actually call this a quantum computer itself?
So quantum computing is a whole different level to all this. So what I'm talking about right now is just quantum physics. And you could say that it is a practical implementation of quantum physics. Because it's
Okay.
exactly what you said. This is like a bigger version of quantum mechanics that you can see and study relatively easily.
So
Because they are on the micron scale or even millimeter scale at some levels.
So this is kind of like so you have these experiments where people actually work with the human mind or like a big brain. Then there are people who try to make smaller analogous brains, either maybe using say fly's brain or something, or trying to completely go artificial. So is this something of that sort? Like the computational power maybe not as dramatic, uh, but you're kind of drawing parallels because this is a more simplified version of what an actual quantum computer would be.
In a way, yes. But in a way, it's also exactly the opposite. Uh, because the simplest quantum system would be like a single atom, but
Hmm.
it is kind of hard to isolate a single atom and study it. Though people do that, and it is also a very well developed field. What we are doing
Hmm.
is we are bunching together very many atoms so that we can see them. So it is at a scale that is more familiar to us humans, so that we can see it, we can control it, and so on. So we are kind of going the other way. So we are not going from the human brain to a mouse brain, but we are going from, let's say, a insect brain to a mouse brain, if that
Okay.
is a
So like yeah,
fair
different
analogy.
stages and yeah,
Yeah,
somewhere in the middle.
yeah.
Right. So with this applications, for someone who's unaware of the powers of quantum computers, what benefits does it give society, or like um, what new things are we learning out of pushing
Hmm.
research in this domain?
I should first say that there is a lot of hype about the applications of quantum computers, and most of it is not true. There is a very specific class of problems that it can solve, and the one very big application that is very, very well known is that if you have a very big number that is a multiple of exactly two primes, two prime numbers, it is known that classically, or with normal computers that we have, you can't factor it back into two prime numbers. It is a very difficult operation. And the thing is, all our encryption systems today are based on this fact that if you have a huge number, which is a multiple of two prime numbers, it is difficult to factor it. But it has been proved that with quantum computing, this is very easily possible. And this fact
These are like
spurred on a
extremely large numbers.
extremely large number. So, yeah, let's say more than, I don't even know what the order is, but yeah, 10 power 25 or even higher.
Hmm.
So it's hard to factor these numbers classically. But with quantum computing, it is shown that it is possible to do it much more easily. And this is what spurred on many government labs and defense agencies and so on to research quantum computing. So it's kind of a arms race on that front. But yeah, we are very far from being able to do anything like that currently.
It's maybe because of the association with like safety systems,
Yeah,
that there's so much hype around it.
yes,
Uh,
exactly.
okay.
And okay, let's say a more benevolent application of it would be to simulate uh, chemicals or organic systems, or like, I mean living systems and so on. Because in the end, all of this is based on the principles of quantum mechanics. So if you want to simulate it, you might have to do it with a quantum computer because they work on the same kind of laws. But as far as I know, this has not been mathematically proven that this is possible. But this is another thing that is driving research in the field.
Cool. So taking you back now by 5 6 years, you're just starting your degree at IISER,
Yeah.
and yeah, like how what things fell in place you felt that led you to this topic and led you to this particular PhD, and yeah, maybe give a brief overview of also what is the curriculum structure in IISER maybe. So maybe I can tell that. So there's like first 2 years you have to kind of study everything, then you narrow down into like physics or chemistry or like specific fields, and then you go into your final year and do a master's thesis. And so but yeah, what was your path in terms of that, like what from first year to fifth year?
Yeah. Uh, yeah. So first 2 years, there is actually not much of physics that is done in the course. It's very basic stuff. Of course, it's very useful and foundational for stuff that comes later, but it is actually in year three where you properly start to learn quantum mechanics, and that was exciting to me because I always wanted to learn it. And at the end of the third year, I got an internship with Sebastian Wooster, who was a
Hmm.
professor at IISER Bhopal, and he did simulations of quantum systems and so on. And yeah, from there it actually really started. Uh, okay, before that I was kind of interested in the topic. I'd read a few books about it and so on. But after doing that internship, I was yeah, more I got some exposure to the field, was introduced to it. And yeah, in the final year, as you say, we have to do a 1 year long master's thesis. And fortunately, I got to do that at CQT Singapore, so the Center for Quantum Technologies in Singapore, where I worked with rubidium atoms to trap rubidium atoms basically, and that was another exposure. At the same time, while I was working in this lab, the other half of my group was working on superconducting circuits, so what I work with now. So there I got to saw very closely what was happening in the field and how people worked and what the research looked like, and it seemed very exciting. So I
Mm.
decided to go into this field, and fortunately I got this PhD.
The rubidium experiment, did it have, was it like using lasers, like optical tweezer to
Yeah,
kind of
it
trap?
was optical, yes,
Okay.
optical laser
And
frequencies.
did it have like a significant overlap, or you just like, there were people in the same lab, so you just used to uh, get involved in their project as well, but, or your project itself had that significant overlap with that?
It was supposed to have a significant overlap with it, but as things happened, the fridge in the lab broke down. Okay, so when I say
Oh,
fridge, it means a cryostat. And
okay.
the idea behind the entire experiment was that the group wanted to couple rubidium atoms to superconducting circuits. But since the fridge in my experiment broke down, that was no longer possible. So we just focused on getting the atoms to work.
Hmm.
But there was another part of the group that was working exclusively on superconducting circuits. And while I was not directly involved with their project, I could see it very closely. So yeah, that was useful. So I had no contribution to it, but it had a
The
huge
learning
effect on me.
experience. You got
Yeah,
exposure, you got people
yeah,
working in that field, and you could
yes,
interact with them.
yes,
So, yeah, nice. Uh, Coming to quantum mechanics itself, typically the perception when people do science outreach is the big names, Einsteins and Schrodinger's, and it's all like pen and paper. Your work is more on the experimental side. So, how is a typical day working in using something like superconductors? You have, like it's not usually depicted in mainstream science outreach. So,
yeah,
what do you use? Like, is there hazardous elements to your work in everyday life? How do you go through that? Yeah, do elaborate on that.
yeah. Yeah, this picture of a lone genius working is very inaccurate. In experimental work, it is a very collaborative, very team-based effort. So we have a huge team of around 17, 18 people who are all working on this. And there are, let's say, three main parts to conducting a experiment, a superconducting circuits experiment. The the first one is to design the circuit that we'll be using.
Hmm.
So this involves stuff like doing CAD design, simulating it using some commercially available softwares. And once you have this design ready, what you have to do is you have to go into a clean room. So what a clean room is, it's a nanofabrication facility.
Hmm.
So there are tools and chemicals and so on that enable you to make these chips at very small levels. So let's say at millimeter scale. So these chips are very tiny, millimeter by millimeter. And there are tools there that enable you to do this. Uh, and the environment in this clean room is very controlled, which is why it's called a clean room. You have relatively much lower particles in the air. The areas are much cleaner. The air is cycled. The temperature is maintained. The humidity is maintained at certain
Do
values.
you wear the bunny suits as well?
Yeah, you have to wear these huge overall suits before you
Nice.
go in. Yeah, so you have to take all these precautions. But it's a very fun part of working on this project because that is where you get to do the hands-on stuff. So you have to fabricate these things with your hands, and that's kind of fun. Once you have fabricated it, uh, you take this chip out of the clean room, and you load it into a fridge, which is what I was talking about before. So it's a
Cryostat.
cryostat that goes to very, very low temperatures, and these low temperatures are on the order of 10 millikelvin. And it's
Hmm.
very hard to explain millikelvin on Celsius scales, but
Yeah.
we can say that it's even colder than outer space. So it's super
Hmm.
cold. And you put this chip into a fridge that can cool down to that temperature. And once you have that, you can control the chip or measure it using microwave signals. So the same kind of signals that are used in mobile phones or Bluetooth or Wi-Fi and stuff like that.
So,
So these are
so
the
when
three
you're in
main
the
steps:
lab, like, do you keep them
design,
away?
fabrication, and measurement.
Sorry,
Keep them away, as in?
as the phones and stuff, do you keep it? Is there like a section where you keep it off? Is there interference from the microwaves?
No, not really. So these are microwave cables that are routed through transmission lines. So there is
Okay.
not much interference at the level that we are working at right now. But if we manage to
Hmm.
improve these things much more, maybe mobile phones will be a problem.
And
And
how do you
yeah,
get to?
you were asking
Yeah,
about the
go on.
safety aspect, right? So in the clean room,
Yes, yes.
you have very many chemicals that are hazardous, and we have to work with it fairly regularly. So yeah, that's an aspect of safety that you have to take care of.
Right. And like the coolant and stuff as well is typically shown to be hazardous, right? Like handling such
You mean
extremely
for
cold.
the fridge?
Yeah.
Yeah, no. So that is not very hazardous because it's liquid helium in
Okay.
principle. And these are very closed systems, so you never get to handle liquid helium yourself. You
Mm-hmm.
control it from the outside using software. So that is yeah, that is fairly safe. But the nanofabrication part is the one that's a bit hazardous.
So, something more on the science side, you have like liquid helium and these coolants, which I don't think go till the microkelvin level. How does a cryostat typically cool it to such extreme temperatures, which, like our everyday fridge or even these coolants won't be able to do because their temperatures are still warmer than what we expect these systems to be maintained at. So, how does it do it? Just the theory side.
Yeah. So millikelvin temperatures,
Hmm.
not microkelvin. So liquid helium
Or
itself,
microkelvin. Like, how do you go in like step by step?
we don't go down to microkelvin, though there are
Okay,
fridges that go that much.
right.
Uh, we only go down to millikelvin, and that's typically okay for us.
Hmm.
Uh, so liquid helium can itself go down to 4 Kelvin, uh,
Okay.
which is again on the order of minus 270 degrees. But
Hmm.
if you want to go colder than that, there is a process called condensation. Um, I'm not sure how
Condensation.
much I should go into it. Yeah, so it's basically like our okay. Let's say you have a glass of water and you heat it up.
Hmm.
So you have some water evaporating out. But what happens because of that water evaporating out is that the water gets colder,
Cooler. Yes.
which is a similar phenomena you experience if you have a drop of water on your hand and water evaporates. Your
We
hand
sweat
feels
to
colder.
cool our body.
Exactly, that too.
Yeah.
Exactly. It's a similar principle just that we do it with liquid helium, which enables us to go colder than 4 Kelvin.
Right. So, is it like fixed in a narrow space and you
Yeah,
try?
it's a very small space.
Okay. Cool. Literally cool.
Yeah, literally cool. It's a bit difficult to explain these things without visuals.
So, coming to the cultural aspect of moving to a different country after 5 years 5 years doing education in India. Also, you got exposed to some a system within Asia itself, like Singapore. Also, something totally in a Western country like Sweden. So, what kind of experience did you see in the professional aspect in work? How were things different in these three settings and in the cultural aspect in these three countries?
Yeah. Okay, so in the professional aspect, even in Singapore, I had a German principal investigator. So my boss was German. So
Hmm.
it's very similar to what I have right now. In the cultural aspect, I really like Singapore because it has a like huge mismatch of mix and match of cultures. There are there are many ethnically Chinese people. There are many ethnically Malay people. There are many Indians in there. So I think you have been to Singapore, so you know what it's like. So all signs in Singapore are in
Yeah,
Chinese,
like
Malay, Tamil, and English.
multilingual
So yeah, it's a
extreme.
multilingual, multicultural place,
Yeah.
and it's a very modern place because of all the banks and multinational companies that are there. So it's a fun place to stay. It's somewhat similar to Mumbai, where I'm
Hmm.
originally from, but still very different. And I especially love the food in Singapore because there is so much variety.
Hmm.
Uh, in Sweden, it's different. It is, I think, very different from, let's say, India or even Singapore. Uh, Professionally, the main thing that I felt was there was very little hierarchy between the principal investigators, postdocs, PhD students, master students, bachelor students, etc. So everyone is more or less on the same level
Hmm.
professionally. And this, I think, was a big difference because in India, at least, we don't see it so much. So there is a very clear hierarchy between the boss and the people who work under him. And that's not there so much here. Uh, yeah, it leads to a different dynamic when working in the office. Uh, Otherwise, there are the standard Scandinavian stuff, but let's say parental leave or mandatory vacations, paid vacations, uh, free education, and so on. That is a bit of a cultural shock when you first get there. But I think those are the good parts.
Like people usually, there are like two factions of people who say like these countries are genuinely good, and then there's this people who say it's like happiness index is very biased. It's not really that case in Scandinavia. So where do you fall in
Yeah, I
this?
think it's genuinely good, and
Okay.
people are like really happy with their lives,
Right.
and they take their happiness seriously.
Hmm.
So it's a very good balance between work and life.
It's
Um,
not,
yeah.
yeah, not living in work itself. Like,
No, no. So I think yeah, the happiness index is quite accurate, at least
okay.
in the Scandinavian case.
Right. And have you been to other parts of Europe, which,
Yeah,
like gave a glimpse of maybe differences within the continent itself?
yeah, somewhat. So I have not been there for extended periods. I just went for a few days to different places.
Hmm.
Uh, as for differences, let's see. So, okay, Germany, Austria were fairly similar to Scandinavian countries, but yeah, I don't want to say that it's the same because obviously there are some differences. I was
Yes, yes.
just not there long enough to notice them, I think. Uh,
Makes sense. Yeah.
yeah, Spain was very different because I think people were far more outgoing and energetic, but also maybe that was because it was peak summer and people were really excited to be outside.
Hmm.
Uh, but yeah, I don't think I've been here long enough to like, notice differences
Like, yeah,
between.
I see people who are in Europe, they're like, suddenly there's sun outside and like everyone's just putting photos of the sun. It's like sun, sun,
Yeah,
sun.
yeah, yeah. Especially in
Especially in,
Northern Europe, that's very common because it's just cloudy and rainy all the time. So if you see the sun, it's a event in itself.
so someone who is in like such a hot topic like quantum computing related work, there's this criticism usually thrown at people who do science outreach, that it kind of gives this false simplified narrative of what exactly quantum mechanics is, and then attracts people into it, and then they kind of are unhappy about things, how realistic how the real picture is different from what science communication and science outreach shows. Uh, do you feel this is a big issue in that sense that science outreach has to change the way how they are popularizing specific topics within the subject, or in the manner they focus on quantum mechanics, maybe more giving more exposure to other fields within quantum itself or something like that? Or do you feel that that is how people can spread science outreach? They have to dumb it down to that level, and it's up to the person to understand at the higher level.
Yeah, so in general, I'm okay with dumbing it down to explain it to a lay audience. Or even the phrase dumb it down is slightly strange because it is our job as people who are funded by public money to explain what we are doing in simple terms to the people who are funding it, so the taxpayers. Uh, so it is in general a good thing that things are simplified and explained to a broader audience. But I think the general hype creation around quantum computing is very detrimental to research and to the progress in the subject. Uh, yeah, there are okay. I can give a few examples of bad science communication and maybe a few examples of good communication. So there was this book by Michio Kaku, who is a very uh, famous science outreach
Outreach,
personality, but
communicator.
yeah, communicator. So he wrote a book about quantum computing, and it was like terrible. It was just most like entirely wrong what he was saying, and it was a problem because he's a very well-known science communicator around the world.
Right.
And when he's saying stuff like, "Oh, quantum computers will solve climate change," that's no, they won't. At least not. It's not clear right now that they will. Uh, yeah. So that's kind of a problem. And just to mention, like he does not work in quantum computing, so I'm not sure how much of an idea he has about what's happening in the field.
Right.
Then there was this paper in, I don't remember what journal it was in, but it was, yeah. So they claimed that they had made a wormhole on a quantum computer, which is again not true. And even established media outlets like Quantum Magazine, who normally have really good stories, good
Hmm.
science stories, they made a whole fuss out of it. And that was again bad for quantum computing as a field. Yeah, but there are some examples of good communication. And for example, Statel Optimize is a blog by Scott Aronson,
Hmm.
and he has worked on quantum computing quite a bit. He's, let's say, one of the smartest people to have worked in the field, and he runs a very regular blog, which is also a lot of other stuff, so politics and so on. But he talks a fair bit about quantum computing, and I think those are very measured opinions, and he's involved like right in the roots of this field, so he knows what's going on.
The
And
the tall claims are kind of impacting research in the field.
yeah, yes. So they're leading to more hype than what is needed. And with hype also comes funding. So there are people who are investing in this without knowing what's actually happening. And
Hmm.
while the field needs funding for sure, but this is not the way to get it.
Right.
Once people realize that most of this is wrong, the funding will stop,
Hmm.
and then it will be a problem to keep things going after that. So that's how
Y-
it's
y-
problematic.
Right. So yeah, coming to personal life, what are your hobbies and how do you de-stress yourself given that PhD is quite stressful? What things do you do to stay away from always be obsessed from work, the work-life balance aspect?
Yeah. So in general, I like reading mostly about history, but also other books. I like reading about Indian history and stuff. Listening to podcasts. So it is fun that I'm on a podcast kind of thing. Uh, yeah, other than that, I used to go swimming a fair bit earlier last year.
Hmm.
This year it has been not so much because I have a conference coming up in March and it's kind of
Yeah.
hectic right now.
Right.
But yeah, otherwise I like reading, I like listening to songs, music, watching movies, TV shows, the standard stuff. I like playing chess
Nice.
online and so on.
Oh, you play chess. Nice.
Yeah, I'm bad at it, but
Me
trying to
too.
learn.
Yeah. Do you still do quizzing?
No, not anymore.
No.
There's not so much of a quizzing culture here. There is a like a there's like a bar quizzing culture,
Ah,
but
yeah.
it's not as fun as what we had in before.
Right. So final question. This is like, of course, a broad ending question I ask because, yeah, as people who have just started off and or maybe in the midway of their research in PhD, uh, what uh, typical advice would you give to people who are in that application cycle phase at the end of their masters or bachelors applying for PhD?
So in general, I would just advise people to apply to as many places as possible, as many
Hmm.
positions as possible, because in the end, it's a yeah, there is a fair bit of luck involved in that process,
Right.
to what you get in the end. So of course, it matters to have a good CV and a good statement of purpose and so on. Uh, but there is still some bit of luck, and so just apply to as many places as possible. And yeah. About applications in India, I don't have a very good idea because I didn't try because
Hmm.
there weren't a lot of or any groups working in this field. So
Right.
I only applied abroad.
Hmm. Cool. So thank you so much. In a busy schedule and in between conference preparation to dedicate time towards this
It's
and
fun.
trying to explain such a heavy and a complex topic in a simple manner. I think you did a good job.
Thank
Uh,
you.
so hopefully more events in the future. If I get to come to Europe, I'll try to
Yeah,
get a lab tour
please
as well.
do. Yes.
Yeah. So yeah, thank you so much. Uh, so I guess I'll like to end it here.
Yeah. Thank you for calling me. It
Please.
was fun to be on a podcast.
I
And
still don't know. Should I call it that? Should I give
yeah,
it
we should
what
find a
name do
name
I
for
give
your
it?
podcast.
Yeah.
Yeah.
Still a nameless entity.
Nameless
But yeah,
podcast.
cool.
Okay.
All
Yes.
right. See you later.
All right. See you. Bye bye.
Yeah. Bye bye.
Bye bye.